Thank you very much for the kind introduction, also for inviting me here. So first of all, I should say that the title changed a bit. So apparently Robert was not the only one to change his title. It was because of, I'll talk a bit about why I changed the title in between, because like somehow to describe the closure of the subset of spacetimes is not as easy as I thought, and we go first steps in that direction. So I guess it should be not too disappointing for you. Okay, so let's structure the talk first. First of all, I want to recapitulate that we have some interesting, let's say, equivalence of or almost equivalence of categories between ordered measure spaces and Lorentzian length spaces, and then, well, I talk a bit about Lorentzian Gromov-Hausdorff spaces, Lorentzian Gromov-Hausdorff convergence, different aspects of it, different possible definitions. Then the point is how to continue from there. And of course, a very nice thing to have would be to describe the closure of the set of spacetimes, but we won't really arrive there. I say a word about that, but the first step towards this is a very stable notion of dimension of an ordered space that is applicable in this situation. Okay, so first of all, this is like an all functors diagram in which many of those topics fit. So first of all, here we have so the ground floor of this diagram is just prescribing a topology on a partially ordered set. So the categories have 3 letters in my world. So this is a category of partially ordered sets, and so we can prescribe topologies on it. I mean, of course, you can think of the Alexandrov or interval topology if you have some derived temporal relation, so to say. And this will suffice for many cases, like for spacetimes, but it will not suffice, as you can think, for, oh, is there shark here? Ah, yeah. For cases like this hard spacetime, like for example, this point won't have a neighborhood of this diamond form, right? I mean, in higher dimensions. Of course, in 2 dimensions, everything is okay. But in higher dimensions, there could be a problem. And therefore, there are different proposals how to prescribe topologies on future causal boundaries. And for example, this was the Andalusian topology, Tor minus, one of the authors of which is here, José Luis Flores. And then there is another topology which I call the beam topology because it was suggested by G. Beam originally. That is metrizable, and we will cling to this one because Tor minus is not a Hausdorff in many cases, and T plus is even metrizable, but T minus is a bit more flexible when it comes to future and past compactification. So I won't go into this here. Just let's say we have a functor from partially ordered spaces to topological spaces. That is applicable in many desirable situations. Then coming to the uppermost floor here, this was like, for me it was 2 or 3 years ago, where I realized that there was some interesting, or 3 years I think, some interesting functor from the category of Lorentzian manifold or Lorentzian spacetimes to Riemannian spacetimes, or subcategories of it. So if you want to prescribe not only metrizable topologies, but actual metrics in a natural way, you encounter a principal difficulty, namely if you consider just Minkowski space and you want to prescribe a metric on it, just say 2-dimensional Minkowski space, where, well, such that this metric should be invariant under all Lorentzian isometries, then this turns out to be impossible, of course. It's like if you fix one point, you see that the boosts, the Lorentzian boosts, just contract arbitrarily close points from here to here into any ball you could prescribe. So there cannot be a natural metric on it, invariant under those morphisms, of course. Therefore, one has to restrict the categories to exclude boosts. And one way to do so is to consider Cauchy slabs, that is regions between two Cauchy surfaces. By this, you exclude boosts from the beginning, and it turns out that actually you can write down functors from Cauchy slabs to Riemannian manifolds with boundary. Actually, they factor over, or they are functors over the identity in the differentiable category. So the diffeomorphism type of the manifold with boundary is taken to be constant. So it's taken to be, it's not changed. Yeah? So how do you construct such a functor? It's just the old idea of Kuratowski, that you just identify points with the distances from the points. I mean, here we have Lorentzian distances, and you cannot take them really. You have to smooth them out a bit. So it's just the name is just the following one. It's phi fp. You take some point x and you associate to it some f concatenated with the Lorentzian distance from the point P. And this is in some LP space of X. And it turns out that geometric properties transfer in a certain way, and a medium-sized miracle makes sure that even there's some curvature bound transferring from the Lorentzian to the Riemannian side. So this is encouraging. And now to the middle floor. Here we have a category I called all, like almost Lorentzian length spaces, which is almost Lorentzian length spaces. I mean, it's just the definition is a bit different because it's just a purist definition, because it's just a set with a function on it, an anti-symmetric function with the conditional inverse triangle inequality, and you derive everything else from it. And I'll show how to do that, or I go a bit deeper into this. And then there is a correspondence to partially ordered measure spaces, which is amazing because those are fundamental structures, right? I mean, for mathematics, orders, measures, and then, I mean, real functions on a set. And we have a nice correspondence between them. And I present it to you in some minutes. And all of this commutes. I mean, this is nice. I mean, whenever everything is defined, then it commutes. So, okay, what is an almost Lorentzian pre-length space? It's just a set with an antisymmetric function. As I said, it's a purist definition, and so it's antisymmetric, and we've seen this already today. And whenever we have a time-like triangle, so to say, or temporal triangle, then there should be the time-like triangle, the inverse triangle inequality. So we can define, of course, a temporal relation from it by just positivity. We can define also a causal relation by just requiring that the time cones the time cones being contained in each other. And then we can define the topology, Tor plus. And I won't go into the details here because it's a bit tedious. But you can imagine that on the subset of points which non-empty future time-like cone and past time-like cone, it's the usual Alexandrov interval topology. It's nothing else, nothing new there. Then there is an ingredient in the traditional definition. Well, I think nowadays one can say traditional definition of Lorentzian length spaces, and it works with a metric. We have seen there is no natural metric in many cases. So how to replace the natural metric by something else? So I I thought it would be maybe a good idea to just define it by a local Lipschitz structure, because anyway, what you want to do is happening in causal diamonds, yeah, or compact subsets. So it suffices to have it locally, and it also suffices to have a Lipschitz class of metrics. And yeah, it's because if you see the definition of the Hausdorff volume and dimension, you see that the Lipschitz class is sufficient. Up to constant, up to multiplicative constant. Yeah, yeah. So this one easily sees that this is sufficient in the constructions, and for example, you can take the class of the Noldus metric. Noldus metric is from 2003. It's the only difference here is that you take the identity square, which was a little mistake in the previous versions, and you can take. I mean, here you take p equal to infinity, and here you take the squaring function, and all of this fits together in a nice way. I mean, of course, you have to put additional hypotheses to ensure that this not only gives an almost Lorentzian pre-length space, but a Lorentzian length space. But this is not part of the data. This is additional requirements you then put. Now, so what is this this functor from distances to measures and orders? I mean, yeah, I don't want to say too much about it, because it will be in Clement's talk, I suppose, as well. So, but just this one transparency. I mean, what do? You take a diameter, and you can take this diameter with respect to local subsets. I mean, this Noldus type metric, for example, and you can take all causal coverings of diameter delta. Yeah, with diamonds of of local diameter not exceeding delta. And then you have some normalization constant, and you prescribe it's just a usual prescription for the Hausdorff measure, with the exception that here you take causal diamonds instead of arbitrary sets or balls or whatever. Yeah, but these parts here are verbally the same as in the definition of Hausdorff of Riemannian Hausdorff measure. And of course, as in the Riemannian case, you have an outer measure induced by that on the Borel subsets. This is Roberts and Clement's work from 2021, and there is a moral inverse of that is really inverse on spacetimes, and it is based on the simple observation that we can reconstruct the dimension just by looking at which subsets this here is maximized. And it is maximized. I mean, if we have some A and C and look for some point B in between, I mean, in Minkowski space, such that this is maximized, then this will be just the midpoint between them. Yeah? And this is, of course, in a sense, stable, and and therefore, this is the simple observation underlying this this construction. So we can reconstruct dimension, and this, of course, is then sufficient to reconstruct the volume, the n-dimensional Hausdorff volume. So and this is this functor FLD you saw in the diagram before. Okay, so we have two nice functors, so to say, defined in general, but and being inverses of each other on the image of spacetime. So it's interesting to see whether they on which larger subset they would maybe be inverse to each other. Therefore, maybe for example, the closure of the subset of spacetimes comes into play. Okay, and but in closure, in which sense? Yeah, we have to prescribe some Where a capital to? Yeah. This JAB is just the diamond. Yeah, that's the definition of phi AC. It's a bit unfortunate that I called too much things phi, but okay, there's another phi from the phi before. Okay, so if we speak about the closure, closure of the subset of spacetimes, then we have to define some notion of convergence, of course. And there, as I said, so this is a general tool I presented to you before, this Kuratowski embedding. And so here, the first thing you could do is just, you could focus on the causal part. I mean, just ignoring the information about actual Lorentzian distance and just taking characteristic functions on the past subset and on the future subset. And taking, for example, there, I mean, this is just the measure of the symmetric difference of the past cones, for example, right? And you can do the same with the future cones, and you can take some mixture. And this is basically what you do in this three copies I took here. This is basically to ensure that the functor is injective. I mean, that you can reconstruct the spacetime from it. And it's a simple, well, I mean, not too difficult calculation that you can actually reconstruct the, for example, spacetime metric or the Lorentzian distance from it. Sorry, not the distance. This is the, if you have volume, you can actually reconstruct the distance, yeah, because you have order and you have volume, and this is enough to reconstruct the metric. Yeah. So okay, but so we have some functor, and it turns out to be a generalized pseudometric on the, so this capital E I in the exponent is somehow this little category of the isomorphism classes. I mean, in many cases, then the morphisms will be trivial only, yeah. But the advantage of it is that it's a set, and I mean the isomorphisms. I mean, there are very few isomorphisms left then here, but only the isometry, so to say. No, only or nothing, but actually, I mean, it's just to make it a set, and okay. Yeah, so this is a generalized pseudometric on this little category, and it's a metric on this on the subcategory which consists of the objects of finite volume causal cones, for example, Cauchy slabs. And yeah, then it cannot take the value infinity, and then it's a true metric on it. And also the n-dimension volume of causal diamonds is then a uniformly continuous function. Now the second attempt to define a metric on this set, so this metric space on the set of isomorphism classes of the Lorentzian length spaces, for example, could be that we just take some f and then the infinity norm. Yeah? I mean, we take the infinity norm here and induce by that. I mean, we can steal the infinity norm from L infinity of x and then just prescribe. I mean, it boils down to taking the essential supremum, and then we have a metric. But this is actually for this purpose the worst approach, because it would not even in the case that this f is a diffeomorphism, be injective. I mean, there are examples, you can construct concrete examples of Lorentzian length spaces in which which you can't distinguish by their induced Noldus metric, so to say. Yeah? There's a concrete example. So if it's not injective, the induced metric cannot be a true metric. It can only be a pseudometric. There are two objects which distance zero, obviously then. Yeah. Okay. And then there's the most conservative approach, in which you just take the one thing that works to define the Gromov-Hausdorff metric and transfer it verbally to the case of Lorentzian distances. And almost all definitions of Gromov-Hausdorff metric fail in this respect. Only one definition survives, and this is a definition by distortion. Yeah? So you can take the distortion. I think it's exactly what I think we did very similar in this in those approaches. You take the distortion of the corresponding Lorentzian distance functions, and you take the infimum of distortions of within the set of correspondences between x and y. Correspondences are just relations which are left total and right total, so to say, surjective to both sides. Yeah? So if there were maps, yeah. So and then it turns out that this actually gives a generalized pseudometric space. And if you, for example, restrict to the space of compact Lorentzian length spaces or pre-length spaces, then this will give a true metric space. And you get a nice estimate between d plus and d minus. Okay, and then you also get that those functors are continuous in a sense. I mean, the functors MCS and FLD going back and forth between ordered measure spaces and Lorentzian pre-length spaces, they are continuous in a sense, yeah, in a very precisely prescribed sense. Here, this K epsilon, it's just, I mean, imagine you have some Cauchy slab. You would just cut away some, so the boundary is trouble, and you just cut away an epsilon piece of the boundary for technical reasons. And then those functors are inverse to each other on the closure on the set of the spaces of global hyperbolic spacetimes because of continuity automatically. And then, of course, it's interesting how large is the closure of the space of the spacetimes, yeah, in this Gromov-Hausdorff space. Okay, there's also a pre-compactness statement involved, like some Gromov type pre-compactness. If we have some uniform diameter bound, and if you have some, so here's a misprint, I think. Here, this ALL, so ALL is always Lorentzian length space, but it should be really replaced by ALP, so which means pre-length space. Yeah. Because here the idea is really to take points, yeah. I mean to take discrete subsets, and it's not length spaces, yeah. But if you have some y epsilon, some finite y epsilon is even finite, and so epsilon dense in all of them, then the set is pre-compact. So this is in direct analogy to the Gromov compactness statement in the Riemannian setting. Okay, so here are just references for the different floors. And for the Gromov-Hausdorff theory, it was like this, within a frame of 2 days, there were 2 articles by Stefan Suhr and Ettore Minguzzi and myself, and basically covering very similar topics of this Gromov-Hausdorff theory. So, okay, now how to proceed further? So as I said, what is maybe essential is to understand the Gromov-Hausdorff closure of the set of spacetimes of global hyperbolic spacetimes. I mean, that would be an essential progress in this business. And then, of course, I mean, in further steps, one could transplant this results on analysis on metric spaces to the Lorentzian setting, and with all the things involved there. Partially ordered measure spaces. Yeah. Measure spaces. I mean, you have an order, you have a measure, and I should say maybe. I mean, why is this category especially interesting? It's better. I mean, in most cases, we are moving in some framework in which we draw some analogies from the Riemannian world and are happy if they work. But here, it's even better. I mean, here. So if you think of metric measure spaces, which, for example, Berger in his book calls the geometry of the future. The geometry of the future. So this is metric measure spaces are in a sense, redundant, yeah, because in most cases you can reconstruct the measure from the metric by the Hausdorff measure. Here it's completely different. It's two completely separated degrees of freedom, which with really physical meaning. I mean, it's influenceability on one hand and overall importance on the other hand. So it's really progress compared with the Riemannian world, say. And then also, okay, so we could examine curvature bounds via optimal transport. I mean, this is a vast topic here on this, covered by many talks on the conference. And one could also look for pointed versions, which I told it in Toronto already. It's just in this case, it should be called double pointed version, maybe. But anyway, so, okay. Yeah, and the first step towards real understanding of the closure of the space of say, n-dimensional manifolds is to find some notion of dimension that is a bit more stable than maybe the Hausdorff dimension, the Lorentzian Hausdorff dimension which we have seen before by Robert and Clement's article. Maybe, I mean, if we are to show, say, stability of the measure, it's maybe a good idea not to include the measure in the dimension already from the beginning. So, so we want to find some notion of dimension of ordered measure spaces, say, for example. And then the question is it in the order or is it in the measure? And I think it's quite obvious that it's in the order. And then, well, then it's about finding some good notions of dimension for ordered spaces. So what is a dimension anyway? We could try to, I haven't found a general definition, so I tried to find, to make up one myself. So if you have a category, and it should be something like a refinement of cardinality, maybe, yeah? So if you have a category, then dimension should be a map from the objects of the category to a totally ordered set, organizing injective morphisms between them. Yeah, I mean, just serving as an obstruction against injective morphisms. Yeah? So, and then we call it a dimension strong if it also is an obstruction against surjective morphisms, and maybe we could call it monoidal if it also respects products. Yeah? Okay, it's just a working definition, yeah? Ah, okay. Ah, yeah. Right. This is a misprint. It's the other way around, of course. Yeah. Of course. Sorry. Yeah. Sorry for that. This is a misprint. Yeah, it's the other way around. Okay. Thanks. Yeah, for one. Okay. Good. So there are people listening to me, still listening to me. That's very reassuring. So then. Okay, so we have a working definition of dimension, and there are plenty of examples of it. For example, you could take the Hamel dimension, the usual dimension, yeah, the linear algebra dimension. This is strong, and it is also monoidal, as also the Hilbert dimension is, yeah, for Hilbert spaces. And they agree on finite dimensional vector spaces. Yeah. Then we have, for example, the category of topological spaces, and then you can take the small inductive dimension, the large inductive dimension, the covering dimension, and all of them would agree on separable metrizable spaces. So there's a large amount of agreement among those definitions here. Then we have the metric spaces, and we have Lipschitz maps with a Hausdorff dimension. It's also meeting this definition. Then we have manifolds and embeddings. And also we have the category, and this is the most important for us, the category of ordered sets and increasing maps with the product order. So the product order is just the order by, so every coordinate has to be greater than the other one. Yeah? I mean, yeah, you know, the coordinate order. And then there's the Dushnik-Miller dimension. I will present it in a minute. Unfortunately, it's not the right one. Because it's not compatible to the other ones. So the Dushnik-Miller dimension is, I don't know whether it's pronounced Dashnik or Dushnik, I don't know. But anyway. So what is the Dushnik-Miller dimension? If we have, it's just the infimum of the cardinality of subsets subsets of the power set of x times x, such that this its subset consists of total orders on x only, and their intersection is the given total, the given order. Not the the given order is not total, but it can be represented as some intersection of total orders. Yeah. So, for example, the Dirichlet-Miller dimension of the product order on Rn is just n. Yeah, it's the intersection of the coordinate orders, and the coordinate. No, it's not. It's not. No, but the coordinate orders are not total. Yeah. So, but what you can do is you take lexicographical orders and you put the kth coordinate at the first slot, and that's total. And you intersect them, and the intersection then means that every coordinate has to be greater than of the one point has to be greater or equal to the same coordinate of the other point. Yeah. So that has dimension n, and in particular, I mean, if we just represent two-dimensional Minkowski space by just the total, just the product order with respect to u and v to the light-like coordinates, then it has dimension 2. So far, so good. So far, so good. But this is not we'll see that it's not the ultimate answer. So what is the utility on X? It's just a map such that into some R to the E I for some set I, for some index set I, such that the order, the given order is just given by fi of x is smaller or equal to fi of y for all I and I. And this is, looks similar to here, but here we have some chain order isomorphic to R, and that's a restriction. It's not the same. That's a restriction. And the Hack-Braun-Gottwald dimension, it's just a recent paper, is then defined as the infimum of cardinalities of y, such that there is a utility from x to R to the y. Okay, and as I said, by this restriction on the character of chains, we have that the Dirichlet-Miller dimension is smaller or equal to the Hack-Braun-Gottwald dimension. And there are also, there are examples where you can see, like the two-dimensional lexicographical space provides an example that has, as it is totally ordered, its Dirichlet-Miller dimension is 1, as every totally ordered space. Yeah? But their Hack-Braun-Gottwald dimension is uncountably infinity. It's more than Aleph 0. Yeah? And this is, okay, I won't go into details here, but it's, you can see this quite easily. So there's a difference, but you still have an estimate. And here's the surprise. I think every talk should contain a surprise. So I try to calculate the Dirichlet-Miller dimension of higher dimensional Minkowski spaces, and the surprise is that R1n does not have Dirichlet-Miller dimension n plus 1. The Dirichlet-Miller dimension is Aleph 0. So here's a sketch of the proof. And also the Hack-Braun-Gottwald dimension is already Aleph 0. It's countable infinity. And also for local, it does not change if I localize the whole thing. It also holds for causal diamonds. Yeah? There's no difference here. So how do we prove that? So we, first of all, we assume finiteness. The first 3 points are to show that it's infinite, yeah, the dimension. So we assume finiteness, and then we use a theorem by Oystein-Ore, or Ure, I think, it's Ure, to get an order embedding. That means, order embedding means that the order on the left-hand side corresponds exactly to the order on the right-hand side on the image, right? Into some product space, Rk with a product order. Then we show continuity of F in this order topology, which coincides with the usual topology on R to the n. And then, I mean, what's the main difference between the orders in those product spaces, product order spaces, and in the usual Minkowski spaces? It's just the form of the cones, right? I mean, whereas in Minkowski spaces we have cones like that. I mean, if we take some point in the boundary of the cone and take its forward cone, then the intersection is totally ordered, which is not the case for those ordered spaces. They look differently. They have some planes, so they intersect in planes. I cannot really draw it here very well, but it looks differently. And then you can use the invariance of the domain and show that with such an order embedding, this set would not be totally ordered, as it should be. It's expected to be totally ordered. So it's infinity, and then it's, and then for the other direction, you can just represent the usual order on Minkowski spaces just by intersection of countably many partial orders corresponding to light-light directions, to rational light-light directions. I mean, imagine like wood carving a cone by rational cuts, or say a sphere. Yeah, I mean, it's just this procedure here. Yeah, and I don't know whether it's illustrating, but anything. But it's yeah, you can do rational cuts, and their intersection will be the sphere, and the same with the Minkowski cone. So it's LF0, the dimension, and this is certainly not what we expect, and it's also bad for having obstructions of embeddings into each other. Yeah, so it's not what we can work with. So I thought one should come up with another definition, and here's the definition. I mean, we just first we have an ordered space. We define a chronological relation by just it's just encoding like that in spacetimes. Null geodesics cease to be maximal after the first cut point, or cut point, or conjugate point. Here it's more cut point, but anyway. So this is encoded here. So for spacetimes it's perfect, so then what we can do is just we take the infimum of the cardinality of a space, which is in a given causal diamond, but not in the cone of P, such that those Q plus minus are in the joint future or past, respective past of A. I mean, I think I should draw a sketch. I mean, if you, for example, I mean, two-dimensional sketch is a bit dull, but here you take just 2 points not contained in the. So here we have 2 points, P plus and P minus, and so they are contained in the joint future of those two here, and also in the past, right? I mean, so yeah. Okay, so this works in higher dimensions as well, just as a definition for general ordered spaces, and it gives you some. So if you then take the lim sub with respect to all diamonds containing this P, this is Q plus, I think, Q plus and Q minus, and this is P. Then you get some notion of dimension. Yeah. So here you have it's just the lim sub is with respect to this natural order on the space of causal diamonds. Yeah. I think later in Didier's talk we will hear something more on it. Here it's showing up already. Okay, so and then the good message is that the good news is that the n-dimensional spacetimes actually have this dimension. In particular, Minkowski spacetime has the right dimension. I mean, it's a notion of dimension for ordered spaces coinciding with the manifold dimension. Yeah, and yeah, okay. I think for time reasons I should not go into the proof. It's not difficult. It's just it boils down to some considering simplices and stable coverings of simplices, it's not really complicated. Anyway, so but this can serve as an abstraction now, as opposed to the Dushnik-Miller dimension, which was useless for us in this respect. We can now actually get abstractions against monotonous injective maps between Lorentzian length spaces. I mean, meaningful ones. And it's just, it's just a 3 lines proof. You take some k-tuple of points around this here and pull it back, and so, and it's what you would expect. Yeah. Okay, it's just the first step towards density of manifolds in the Gromov-Hausdorff sense. I should say a word, just 1 minute about it. There is some, so at this point, I'm really very confident that there is a good density statement of Gromov-Hausdorff with respect to Gromov-Hausdorff distances of spacetimes. The point is only how meaningful it is for our question of Hausdorff volumes. And the point is the following one: you can have perfect Gromov-Hausdorff convergence even for Riemannian length spaces without the Hausdorff volume converging, as you may know, and even with curvature bounds. Yeah, I mean, for example, take this example of a torus, and you take n points on the torus, in which you take the connected sum with a smaller torus, say of it's just k times S1 times S1 with a standard one, and then you take here xn is equal to the standard one, T2 of 1, and then you pick n points like equally distributed here, and then you get T 1 over 1 over square root of n n times. Okay, so those are compact geodesically complete length spaces with upper curvature bound, and they are all 2-dimensional, and they converge in the Gromov-Hausdorff sense to the standard unit torus, but still the volume is different. The volume is always 2 and not 1. So it's, yeah. So one needs something more. One needs some injectivity, some good notion of injectivity radius in this business, and this is what is to be done in the Lorentzian case as well. And then you are in business. Then you can say something about those two functors being inverse on to each other on the closure of this spaces. So with appropriate geometric bounds, I'm pretty sure that you can do this and say that the functors are inverse to each other, and this will be a work in progress, I should say. Yeah, but here you have seen some first steps, yeah, towards dimensions, and maybe I hope it's interesting for you anyway. Okay, I think that's everything I wanted to tell you.